Hi all, welcome to my lecture on distribution of nucleons in the nucleus, or in other words, we'll discuss what is nuclear density. We saw in the previous class that from scattering experiments, a whole lot of information can be collected about a nucleus. It is possible to estimate the size of the nucleus, and we saw the estimation of radius of various nuclei. From scattering experiments, it is also possible to estimate the structure of a nucleus, how charge is distributed within the nucleus, how nucleons are distributed within the nucleus. All this we can get to know from scattering experiments. If we consider the interaction of an electron with a nucleus, this is essentially what happens. Here you have an electron wave coming in with wave function psi I exponentially e raised to I k dot r, and this is your nucleus, and upon scattering the electron wave changes direction, wave vector becomes k prime, and your wave function is e raised to I k prime dot r. If it is an elastic scattering, there is just change in the direction of motion of the electron, and its kinetic energy remains pretty much the same. So the magnitude of k and k prime are the same, but the directions are different. What is the reason for such a change? It is due to interaction of the electron with the nucleus. Electron is a charge, and your nucleus is also a charge distribution, and it is owing to this interaction that there is a deflection for the direction of motion of the electron. Now, what sort of an interaction happens between an electron and a nucleus? Of course, the interaction is Coulombic interaction, and you have the Hamiltonian H prime, the perturbation. It's nothing but the potential energy of interaction of the electron and nuclear charge, and it is given by this thing, integration over the nuclear volume rho r prime d tau prime divided by 4 pi epsilon 0 r minus r prime times minus e. So you can imagine the picture like this. You, with respect to an origin, the position of the electron is given somewhere like this. So your electron is approaching, and this r vector r is a variable. At some point of time, just imagine that the electron is somewhere here, and you have a nucleus, and you consider an elemental volume in the nucleus d tau prime, and if the charge density is rho r prime, then over the entire volume, the total charge would be rho r prime times d tau prime. And of course, the potential energy of interaction of two charges is given by product of charges divided by 4 pi epsilon 0 times separation between the charges. Separation between the electron as the nuclear charge is mod r minus r prime. So this is actually the potential energy of interaction of the electron and nuclear charge rho r prime d tau prime. Now, for any transition from an initial state psi I to psi f, quantum mechanically the probability of such an interaction is given by Fermi's golden rule, and probability is proportional to expectation value of h prime mod of that square. And this is how you write this expectation value as over the entire volume psi f star h prime psi I d tau. And instead of your h prime, you just plug in this expression, and you get something like this. So d tau prime is actually the elemental volume within the nucleus, and d tau is the entire space. So please don't confuse with d tau prime and d tau. And so from this expression, we understand that k is known, k prime is also known, 4 pi epsilon 0, everything is known, charge E is known, and everything is known. So if we know rho r prime, then it is possible to evaluate the probability by which the electron wave undergoes scattering in various directions. Okay, but here our problem is we are not aware of the nuclear charge density. We don't know that. That is the unknown, and that is what we need to evaluate. But experimentally, we know the probabilities of electron wave getting scattered in different directions. Okay, in a scattering process, we have seen that sometimes the electron wave goes unaffected, sometimes the electron wave gets slightly deflected, and sometimes it gets largely deflected. So experimentally, we actually know the probabilities of the electron wave getting scattered in different directions. So we know the left hand side. All we need to know is the unknown factor rho r prime in the right hand side. So this is basically Fourier integral, and if we do the inverse Fourier transform, we can evaluate rho r prime. So this is basically a Fourier transform, and if you do the inverse Fourier transform, it is possible to evaluate rho r prime. So doing that, um, we see that rho r is something like this. For it is depicted for three different nuclei. For oxygen, which is a lightweight nuclei, for tin, which is a medium weight nucleus, and gold, which is a heavy nucleus. So you see that nuclear charge density, or uh, charge of a nucleus comes from its protons. So this is how protons within a nucleus are distributed. Okay, so you see that the distribution of protons or the density is fairly constant up to a particular distance, and it falls gradually. This is true for this nature is true for all the three types of nuclei that we have depicted here, and we see that it's true for all the nuclei available. For all nuclei, charge density is fairly constant up to a particular distance, beyond which it falls gradually. Now, if we just assume that, but inside a nucleus, there are protons as well as neutrons. So, if we just assume that neutrons too are distributed in pretty much the same way as protons are, then making that assumption, you can see that the nucleon number is A, proton number is Z. So the mass density of the nucleus will of course depend on the number A, and charge density will depend on Z. So if we assume that the distribution is pretty much the same, the mass density can be written in terms of charge density like this. That is, you scale the charge density by a factor A by Z, you get the mass density. This is under the assumption that the mass distribution within a nucleus is pretty much in the same fashion as charge is distributed within a nucleus. Now, if you plot the values of mass density along the y-axis with R, for the three nuclei we saw before, oxygen, tin and gold, you see that nuclear density again or the mass distribution within a nucleus is a constant is fairly a constant up to a particular distance beyond which it gradually falls. We also see that mass distribution density or nuclear density is a constant at the center of the nucleus for all the three nuclei that we have taken here, and it's true for all other nuclei too. This constant density is approximately 0.17 nucleons per femtometer cube. And see, if we had obtained a graph which is a straight line, we could fit it with an equation y equal to mx plus c. Now we have obtained such a graph whose shape is like this. The value is uh, starting from a constant value. It is maintaining that constant value up to a particular distance, and it is gradually going to zero. It's not an abrupt end. The best fit for this graph is obtained when you write your density as rho is equal to rho 0 divided by 1 plus exponential r minus r by a. Okay, so your rho is the density at different distances. Rho naught is the density at the center, and it's a constant value. And your capital R is the distance at which density falls to half the maximum value. Okay, that is capital R. And A is a factor which tells you how sharply your density falls. We will see what all these parameters mean as we progress in this lecture. So it is like if your A is small, it just implies that your density falls sharply. We'll just see everything. So this is a typical plot of nuclear density with distance. And as mentioned, your nuclear density starts from a constant value. It maintains that constant value up to a particular distance beyond which it gradually falls. And the value of R for which nuclear density becomes half of initial value. Suppose this is your initial value rho 0. The distance at which it becomes rho 0 by 2. That distance is called capital R. Okay. Now if we consider 2 points on this graph, one point is where your density has decreased by 10%. A decrease by 10% would mean the value of density is 0.9 rho 0. And another point which you have considered in this graph is a decrease by 90%, which means your density is 0.1 rho 0. So we have taken 2 points on this graph. One point, the position at which density is 0.9 rho 0, and another point where density is 0.1 rho 0. Okay. Now we are going to measure this distance, the distance for which density falls from 90% to 10% of initial value rho naught. Okay, we are going to find this distance over which density falls from 90% to 10% of initial value. Okay, so let's see at what distance R does your density become 0.9 rho 0. We need to find this distance as well as this distance. Okay, so initially we are trying to find out what is the distance from the center of the nucleus for which nuclear density becomes 90% of initial value. So we take the equation rho equal to rho 0 divided by 1 plus exponential r minus r by a, and we put rho as 0.9 rho 0. So we'll get our expression like this. Left hand side and right hand side, you have one row 0 which will cancel with each other, and you can take this denominator to this side and your 0.9 here. So your expression will be like this, and from this if you evaluate exponential r minus r by a, 1 divided by 0.9 is 1.1, and minus 1 it becomes 0.1, and you get your small r as capital R minus 2.303a. Approximately, let it be capital R minus 2.3a. So this is the distance from the center at which rho 0 becomes 0.9 rho naught. Okay, so if this is your position of capital R, then this is 2.3 times a less than your capital R. Okay, now we need to find out at what distance does density become 0.1 rho naught. So what do? You plug in 0.1 rho naught on your left hand side, and you evaluate your your small r, and you get the expression as small r is r plus 2.2a. So this is your point where your density becomes 0.1 rho naught, and that is greater than r by 2.2a. So fairly you can see that the separation is approximately 4.4a. So you can picturize your nucleus as something like this. Centrally you have up to a particular distance, the density is fairly a constant. Okay, so you have a central core for a nucleus where the density or the number of nucleons per unit volume is a constant everywhere. Beyond a particular distance, that is only up to a particular distance, the behavior is like this. The density is constant only up to a particular distance. Beyond that, it gradually falls. So over a distance of say 4.4a, your density falls from 90% of initial value to 10% of initial value. So you have a shell outside this core, and in the shell region, as distance progresses outwards, as we progress outwards from the center of the nucleus, we see that density decreases, and finally it becomes 0. So actually, if you are imagining the nucleus, you should not have a picture that it is a rigid sort of a ball with rigid boundaries, with sharp boundaries. It is not so. A nucleus uh, does not have a sharp boundary, its boundary is diffused boundary. So this distance, approximately say 4.4a, that is the distance over which your density falls from 90% to 10% of initial value. Okay, that uh, distance is called skin thickness or cap thickness. Okay, from experiments, we have observed that the factor A is approximately zero point 0.5 femtometer. So actually, skin thickness is a constant. Say approximately 4.4 A means 4.4 times zero point 0.5, which gives you 2.2 femtometer. So since A is almost the same, the skin thickness is found to be almost the same for different nuclei. Okay, it doesn't depend on what nuclei you are taking. Skin thickness is almost the same for all nuclei. And uh, it's possible to evaluate R for various nuclei, and we see that R has a dependence on mass number as R is proportional to A raised to 1 by 3. And if you remove the proportionality constant, it is R equal to R0 A raised to 1 by 3. And this R0 is a constant value of 1.2 femtometer. So you see that the only variable uh, which decides your radius is mass number, and R is proportional to A raised to 1 by 3. Now how did we get this? We got this from this relation, that is nuclear density is fairly constant up to a particular distance. So when we take density is a constant, we can write A divided by 4 by 3 pi R cube is approximately a constant, and this is how we arrive at the uh, proportionality relation. R is proportional to A raised to 1 by 3. So for different nuclei, you have different number of nucleons, and if we look at this picture of nuclear density, we can see that nuclear density starts with a constant value at the center for all nucleus, and the distance over which density is a constant, that is different for different nuclei അല്ലേ? ഇപ്പോൾ ഓക്സിജൻ ന്യൂക്ലിയൈ എടുത്തു കഴിഞ്ഞാൽ വളരെ ചെറിയ ഡിസ്റ്റൻസ് വരെ മാത്രമേ ആ കോൺസ്റ്റന്റ് വാല്യൂ മെയിൻറ്റെയിൻ ചെയ്യുന്നുള്ളൂ. അതിനുശേഷം ന്യൂക്ലിയർ ഡെൻസിറ്റി പെട്ടെന്ന് തന്നെ കുറയാൻ തുടങ്ങുന്നുണ്ട്. ടിൻ ആവുമ്പോഴേക്കും കുറച്ചുകൂടി ഡിസ്റ്റൻസ് വരെ ആ കോൺസ്റ്റന്റ് വാല്യൂ മെയിൻറ്റെയിൻ ചെയ്തിട്ട് പിന്നെയാണ് ഡെൻസിറ്റി കുറയുന്നത്. ഗോൾഡ് ആവുമ്പോഴേക്കും the distance over which the density remains a constant also is greater, and then density falls. അപ്പോൾ ആ കോറിൻ്റെ സൈസാണ്, സെൻട്രൽ കോറിൻ്റെ സൈസാണ് പല ന്യൂക്ലിയൈക്കും ഡിഫറെൻറ്റ്. മനസ്സിലായോ? സ്കിൻ തിക്നെസ് കോൺസ്റ്റൻ്റ് ആണ് എന്ന് പറഞ്ഞു. എല്ലാ ന്യൂക്ലിയൈക്കും പുറത്തെ ആ ഷെല്ല് ഒരു we saw there is a shell for every nuclei over which your density falls from 90% to 10% of initial value. ആ സ്കിൻ തിക്നെസ് ഇസ് എ കോൺസ്റ്റൻറ്റ്. അത് ഏത് ന്യൂക്ലിയൈ എടുത്താലും, ഓക്സിജൻ എടുത്താലും ടിൻ എടുത്താലും ഗോൾഡ് എടുത്താലും എല്ലാത്തിനും അത് സെയിം ആണ്. പിന്നെ ആകെ വ്യത്യാസം വരാനുള്ള സാധ്യതയുള്ള ഒരു സാധനം എന്ന് പറയുന്നത് ആ സെൻട്രൽ കോറിൻ്റെ സൈസാണ്. സെൻട്രൽ കോറിൽ ഡെൻസിറ്റി മാറില്ല. അത് ലൈറ്റ് ന്യൂക്ലിയൈ എടുത്താലും മീഡിയം വെയ്റ്റ് ന്യൂക്ലിയൈ എടുത്താലും ഹെവി ന്യൂക്ലിയൈ എടുത്താലും സെൻട്രൽ കോറിൻ്റെ ഡെൻസിറ്റി സെയിം ആണ്. പക്ഷേ സെൻട്രൽ കോറിൻ്റെ ഡയമീറ്റർ അത് വ്യത്യാസമായിരിക്കും. സോ if we are using this formula to evaluate the radii of various nuclei, you see that with mass number, if you take mass number as 27, your radius is 3.6 femtometer. If you consider nickel nuclei, radius is 4.7. If you take a nucleus with 100 nucleons, it is 5.6. And if we take uranium, we know how many nucleons are there, 235, becomes 7.4. So you just look at the variation in sizes. Say if you consider hydrogen. If you consider hydrogen nucleus, the radius is 1.2 femtometer. It has only one nucleon. And if you consider uranium, which has 235 nucleons, the radius is 7.4 femtometer only. So if you consider the change from hydrogen to uranium, the size differs only by a few femtometers, whereas the number of nucleons have largely increased. For hydrogen, there was only one nucleon, whereas for uranium, you have 235 nucleons. So even when the nucleon number increases rapidly, the size doesn't vary so rapidly because the dependence is on A raised to 1 by 3 only. Okay, so for very light nuclei to heavy nucleus, nuclear size doesn't vary by orders. It's actually in the same order. 2 ഫെംറ്റോമീറ്ററിൽ നിന്ന് മാക്സിമം പോയി കഴിഞ്ഞാൽ ഒരു 8 ഫെംറ്റോമീറ്റർ ആവുന്നു. ആ ഒരു 5-6 ഫെംറ്റോമീറ്ററിൻ്റെ ഡിഫറൻസ് മാത്രമേ വരുന്നുള്ളൂ ന്യൂക്ലിയർ സൈസിന്. Now, within a nucleus, there are so many positive charges closely packed with each other. Now, why is it that there is no repulsion, or what holds so many positive charges together in such a small volume? അതൊരു ചോദ്യമാണ്. കുറേ പോസിറ്റീവ് ചാർജുകൾ ഇങ്ങനെ അടുത്തടുത്ത് അടുക്കി വെച്ചിരിക്കുന്നു. എന്തുകൊണ്ട് ഈ പോസിറ്റീവ് ചാർജസ് ഒന്നും ഈ പറഞ്ഞ പോലെ തെറിച്ച് ദൂരെ പോകുന്നില്ല? റിപ്പൾഷൻ കാരണം. വാട്ട് ഹോൾഡ്സ് ദെം? അപ്പോൾ വാട്ട് ഹോൾഡ്സ് ദെം, ദാറ്റ് ഇസ് എ കീ ടു ന്യൂക്ലിയർ ഫിസിക്സ്. It is nuclear force which holds the nucleons, such so many positive charges against Coulombic repulsion. And there are so many properties of nuclear forces which we will see later on. So this is actually the picture of the nucleus. It is actually a very diffused uh, boundary object. It doesn't have a sharp boundary. The central core is of constant density. The central core size varies for different nuclei, and the shell thickness or the skin thickness, that is the same for all nuclei, irrespective of whether they are light, medium weight, or heavy nuclei. This is one way of estimating your nuclear density through scattering experiments. There is another method to estimate nuclear radius, which we will see in the next lecture. Thank you.